This video is for 17.1, Radical Expressions and Functions. Basically 17.1 is about square roots and cube roots. A square root, like the square root of 100, is 10. The reason why is if I take 100 and I try to figure out what times what makes 100, then it would be 10 times 10, which is 10 squared. When you have a square root, it is understood that this is an index of 2. An index means how many of those numbers you're going to multiply to get that. So you can see that these are the same. Square roots, they're easy to use your calculator, and that's fine that you use your calculator for that. When we get into variables, that doesn't work anymore. And so that's why I'm showing you how to figure them out without using your calculator. Perfect squares are easy. If they aren't perfect squares, then you use your calculator. So let's say you have like the square root of 25. Well, that's the same as saying 5 squared. And so remember, it's understood that there's a 2 right here. So I know that the square root of 25 is 5. But think about this for a second. Why couldn't you have a negative 5 inside here? If you had a negative 5 and you squared it, that would still be okay, because negative 5 times negative 5 would make positive 25. So these two things are the same. Okay, so when we think about it being a variable, if I say the square root of x, then I need to say, like if I have x squared and I take the square root of it, I need to say that it's the absolute value of x, because it could be negative 5, and then when I go to solve it, it's a positive 5. So it could be a negative x that's in there, and then I go to solve it, it's a positive x. So the square root, when you take the square root of something, you're not going to get a negative. If you have the square root of 36, you're going to get 6. But inside this thing right here, that could be a negative 6 or a positive 6 that's being squared to make 36. We don't have to worry about it when it's numbers. You have to worry about the absolute value when it's variables and when they're taken to an even power. Okay? We'll talk a little bit more about that as we go through. So I said in your calculator you have a square root button. You need to get familiar with that because some of the numbers are huge. Like, what if I took the square root of, let's say 256? You could sit there and try and figure out what times what makes 256. And remember that what times what, it has to be the same number. It can't be 2 times 100 and something. It has to be like 50 times 50, 35 times 35 or whatever. And that sometimes can get overwhelming. So figure it out in your calculator how you use the square root button. So the square root of 256 is 16. Some problems that you'll run into look like this. 256 over 25. And they'll have numbers within this radical. This is called a radical. Okay? So if that radical comes all the way down and all the way back up, that is the same thing as saying the square root of 256 and the square root of 25. Sometimes it works if you simplify inside here and then take this and then try to figure out the square root if it's a perfect square, but it gets kind of ugly if you're doing it by hand, okay? And eventually with variables you have to do it by hand, so that's why I'm going through this. So if the radical comes all the way down and all the way up, you can separate into 2 different pieces. So the square root of 256 is 16. The square root of 25 is 5. So then your answer is 16 over 5. You can simplify that if you want. You don't have to. Usually we don't. We leave it in improper. So if I have a cube root, what if there's a 3 in here as an index? Well, if I have the cube root of 8, that means I got to find out what times what times what equals 8. I need something to the cube root, and I need that something to equal that 8. So what times what equals 8? What times what times what? Well, that one's 2. That's a little bit harder to think about because 2 times 2 times another 2. 2 times 2 makes 4, and 4 times 2 makes 8. So when you have other roots besides squared, like squared, they don't tell you what the index is. It's automatically a 2. But when you have other roots, they'll write it in there. So let's try another one. So what about the cube root of 64? If you don't use your calculator, don't use your calculator right now so that you understand what it's asking, because again, eventually we're getting to variables. You're looking for something times something times something. You can think about it like this. I always think about it like this, but you could think about it like this. I need to know that times that times that. I just got to make sure all the 3 of those things is the exact same thing. So 64, let's think. 4 times 4 is 16, times another 4 is 64, so it must be 4. So I can put a 4 in there. So the cube root of 64 is 4. So the answer to this problem is 4. So once you set it up, this way, it's easy to see the answer because it's whatever's in here. Okay. So how about, let's see. How about the cube root of b cubed? Well, think about it. If the cube root of 4 cubed is 4, then the cube root of b cubed has to be b. Because remember that I showed you that the index and the exponent, if they're the same, then whatever number you wrote here is the answer. So let's try this one. How about if you have the cube root of b to the 6th power? Well, think about b to the 6th power. Think back to your exponents in chapter 12, I think it was. We know that b cubed times b cubed, b cubed times b cubed is the same as b to the 6th power. So if you think about that, that means that I could take the cube root of each one of them. So that's the same thing as saying 3, the cube root of b cubed times the cube root of b cubed. Well, I already know the cube root of b cubed is b, so that means the answer must be b squared. Now the book shows it like this. Let me show you a different way. You know, remember how in before where I was trying to get the index and the exponent to be the same? Well, you know b squared cubed is b to the 6th. So you could think about it that way too. So 2 different ways to think about it. You get the same answer no matter what. How about the 5th power of y to the 5th? Well, we learned that the index and the exponent, if they're the same, then I have the answer. It must be y. Just like the 6th power of x to the 6th is x. Okay, but the one thing, if you have even exponents, remember that x could be a negative because it will a negative times a negative equals a positive. So if you have an even number of exponents, then you have to say that it's the absolute value of x. Because you know that, like if you have the cube root, let's just put a number in for x. Let's call it 2 to the 6th. You know that equals 2. But if I put, see if I can do this, negative 2 in there, and I take it to the 6th power, I'm also going to get 2. So 2 different values for x, and I got the same answer. So we always have to put absolute values around it if there's a variable inside and it's an even power. So I always forget to. So you don't have to do it on odd powers because then you can't get a positive if you multiply a negative number an odd number of times. So y squared, square root of y squared is absolute value of y. Cube root of y cubed is just y. But the 4th root of y to the 4th is y with absolute value. So it's those even exponents that you need those absolute values. Absolute values just make it positive. Absolute value is like the distance from 0. So let me see. How about this one? Y to the 12th. So in your head, you just got to think. How many y's could I get? Now this is like if you're getting confused with this when there's no index out there, just write it in. Remember, it's understood if there's just an absolute, if there's just a radical, that it's a 2. Okay, so I'm looking for something in here that I can multiply twice. Well, y to the 6 times y to the 6 is y to the 12th. So that means it must be y to the 6. Or, again, whoops, you can think of it like the textbook taught it. Y to the 6 squared. That might help you because your index and your power are the same. I don't know why I tend to think of it this way. It helps me every time I have 2 groups of those and I know it's the answer. Okay. So, what about bringing in last chapter? What if I have the square root of x squared minus 4x plus 4? So remember that the index is 2, but the book won't put that. The textbook company won't write a 2 there. So you've got to think about, what can I put in here? How can I make this into 2 groups of something that are exactly the same? Well, I know that x squared minus 4x plus 4, I have to find a number that multiplies to 4 and adds to negative 4 to find 2 numbers. Well, that's negative 2 and negative 2. So I know it's x minus 2 times x minus 2. So expect that in the quiz you might get something like this because you've already learned how to factor those. So now that you have the 2 factors, you have 2 items, two binomials inside that square root, so that means the answer must be x minus 2. Here's another one for you. Not like that, but how about the cube root of 213 x cubed? Well, the x cubed part, this cubed goes to this x only. So that's kind of easy because I know my answer is going to have an x in it. Okay, but the 213, I'm going to have to figure out what times what times what makes 213. You can use your calculator for that. 6 times 6 makes 36. So, and is that right? Let me check. And that's not a perfect square. Let's change this to, sorry about that. Let's change this to a 6, 216. Let's see, 6 times 6 makes 36 times 6. Yeah. So that would be a perfect square of 6. So I know that 6 is in my answer. So my answer is 6x. One more problem. How about the cube root of 729 and x plus 2 cubed. Now this cubed only goes to this x plus 2. If it went to the 729, there would be parentheses around it. So I want to think about that. So I know that this part of the answer has to be x plus 2. Because remember, the cubed and the cubed root will cancel themselves out. I just got to figure out what times what times what equals 729. Okay, and that's going to be 9. So my answer is 9 times x plus 2. I don't need absolute values because it was cube root. It wasn't an even root.